by the way, instead of spending all the time I should have spent working on my talk, I spent a lot of it trying to find the right accurate font for this slide. And I spent like 4 hours looking for it. And anyone who says it's Arial Black, like, it's not. It's not. They're just wrong. It's Franklin Book. It's the closest that you can get. People know who Run DMC is, right? Yeah. Like, OK, all right. Probably should have led off with that. 'Cause I don't know if it's dating me or what. But all right, so I'm going to talk about basically last year, everything that's happened in the universe of PuppetDB. This is me. By the way, animated image support in Keynote, total game changer. Like, iPhone 6 Plus has nothing on this. Like, that's amazing. So that's me. That's my email address. That's me on Twitter. So if you have any other questions or anything like that, more humorous pictures, feel free to send them my way. But I've been at Puppet for a couple of years. And before that, I was a big user of Puppet. I ran it for a long time. I've been around the conferences for a pretty long time. Now I'm director of engineering, making, I don't know, the brutal reign of me has now begun. And you will feel the wrath of my terrible technical decisions for years to come. OK, so first off, how many people are currently using PuppetDB for anything? Oh, wow. So a lot of people. OK, so I'll try and blast through this relatively quickly then for the sake of people that are on the video. But a quick recap is you've got an agent, you've got a master, and you've got PuppetDB. So what happens here? Basically, agent does some magic. It'll collect facts about itself using C-factor, hopefully, which I encourage you all to play with. Everyone knows what facts are. One interesting thing that's happened recently is facts can now be structured, so they aren't necessarily just flat strings as values. You can actually have arbitrarily nestable data, which is pretty cool. So you get all these facts that get sent over to the master. And then the master says, OK, well, I'm going to take these facts, and I need to put that as input into the whole compilation process in order to figure out what the config for a system actually looks like. But for the purpose of this talk, the more interesting thing is we actually want to persist those facts so we could do something interesting with them. Like we want to query them. It's a lot of valuable, juicy inventory data that we can do good stuff with. So we send a copy to PuppetDB, which expands and then destroys it. I really should have put like a smiley face because it enjoys, it's like a bot snack, but for PuppetDB. So anytime facts actually happen and are generated from agents, they all, by virtue of going through the master and by virtue of being involved in the compilation process, it eventually makes it over to the PuppetDB side where it's now persisted, and then everything is good with the universe. The next thing that happens is the master can take all the facts that it's collected from the agent, and it could say, all right, well, now I have all the inputs that I need. I can actually produce a catalog. And the catalog is sort of the name we have for the artifact that the compiler produces. So it's basically the set of all the things that it's going to be configuring on the agent itself. So that's all your files, all your packages, service declarations, all that kind of good stuff, and there are relationships between all of those things. So it generates that catalog. And then what it'll do is kind of simultaneously, it'll send one copy of it over to PuppetDB, who loves it. And then the other copy of it goes to the agent. And what the agent does is the agent actually takes that catalog and does what one would think an agent would do with it. It actually has this kind of bill of materials that says this is how your system is supposed to look. And the agent takes care of actually making the system look that way. I like to think about it sort of under the hood that the agent takes as input this catalog, and then it starts doing all this magic. This is from Ghost in the Shell. And I saw that a long time ago, and I finally found this picture, and I put it in here, and I was like, oh, that's so awesome. That's super cool. And then I thought, like, why do you need the super fast fingers? Like, you should just interface beyond the keyboard, like at a device driver level or something. I don't know. Maybe it's NT4 or something like that, and it doesn't work. So the agent, presumably at this point, has actually configured your system to look the way that it's intended to look. So what ends up happening after that is it generates a report. So the catalog kind of represents the utopian vision of the world, right? Like that has all your desired state for everything that you care about. Okay? So the report represents the crushing despair of reality, and it tells you what actually happened. So it's like, hopefully in an ideal universe, everything is exactly the way that you thought it would be, right? Like the agent says, I've never had to do anything at all. But oftentimes what happens is configuration changes need to be made. So that all gets codified inside of a report. So the report gets sent back to the master, and you can guess what happens here. And everything is good. And you have a healthy PuppetDB with a shiny coat, and it will live long and provide you years of companionship until Oracle end of life its runtime. It's too soon. It's too soon for that. I had a conversation with someone, a subject of end of life. I had a conversation with someone the other day who said that they had like 100 RHEL 4 systems still, and they had a couple of RHEL 3 systems, and some Red Hat 6. So stuff is, we're screwed forever, is basically what I'm saying. So it's really great to have all of this data, and as many of you who happen to run databases in production, obviously you know that all software is extremely well behaved, and especially software that acts as any kind of sink for information, and it will never go out of control and destroy everything. So I kind of visualize it like this. Like PuppetDB is fantastic, so I have my master. I want all my catalog stored in here. I'm going to send a catalog over to it, and it happily ingests it. And OK, now it's a little bit larger. The problem, though, is that if you have a lot of systems, you're going to be sending catalogs over pretty regularly. So for example, if you have 1,800 systems and a 30-minute run interval for your Puppet agents, then on average, you're going to be getting one new catalog produced every second. And 1,800 systems really isn't that outlandish anymore. So you can kind of keep going, and you got to take the good with the bad, because on the one hand, your information that is able to be queried and called upon, it's the information that's being warehoused, it's kind of becoming richer. You're getting more information, more data that you can call upon to do interesting things, interesting queries. You can correlate it with other tools, all that good stuff. But obviously, something has to give, and you just can't keep throwing stuff in there forever, despite the fact that it's a more vibrant source of information for you to do things. So eventually it will explode from sort of overwhelming intelligence. It just has so much information in it, it doesn't know what to do. And it kind of freaks out. I literally watched this for like 20 minutes on a loop. It was quite amazing. So what I would say here is, and everyone's run into a situation where they have some kind of data sink that eventually exhausts all of its storage space, or kind of expands to consume all the resources in the environment, right? So my axiom one of the axioms I try to internalize, when it comes to sort of designing software systems, is that ideally they should be pretty self-regulating, right? That's a goal. Obviously even the stuff I build is not 100% there. Most of the stuff people build isn't 100% there. But I definitely think software that's intended to be more self-regulating is generally less of an operational nightmare, right? I think that's probably not a controversial statement. So how do we get there for PuppetDB? So what I'm going to talk about now is basically the ways in which we've tried to engineer it so that it is more self-regulating than one might think by initial appearance. So let's say that I've got PuppetDB, and that's kind of represented by storage, and I've got catalogs for 3 systems. I've got foo, I've got goo, and I've got bar. So what I could do is just continue storing every single catalog that I've ever seen for every single system at a rate of 1 per second if I've got 1,800 machines, and then everything will explode, as you've seen. So instead, we kind of take a shortcut and we think, well, OK, at least currently, is there a huge amount of value that people get out of storing a large number of historical catalogs? Probably not. So what we actually do is we just figure, OK, well, I had a catalog for bar. I don't really need that anymore. And I'm just going to plop the new one in place. And we can just do that within a transaction, and it's all atomic, and then everything is great. But that's one way that one can make sure that you don't just have a runaway system that expands to take up all the disk space that you've got, right? Because it's there's an inherent limit in how much stuff we're going to store, which is kind of nice. And I think about that as basically self-regulating storage for things like catalogs and for things like facts. Facts basically behave the exact same way. I get a new set of facts for a system. Do I really need to store all the old stuff? At least in this system, I don't know. Maybe, maybe not. Right now, it certainly doesn't. So then, we just go ahead and we actually replace the old version that we had. I think you can see this in other areas. For example, reports don't really work like this. So for reports, what people actually want is they really want historical data, right? Because that's the whole point of having reports stored, is you're rarely just looking at the most recent one. Maybe 90% of the time you're looking at the most recent one, but it's very common that people want to go back in time, at least a little bit. So there, what do we do? And I think we kind of take a fairly common sense approach, which is, all right, well, let's say for bar.com, I've got a number of reports that are actually stored. I get a new report that comes in. What I can do is actually just destroy the oldest one, and then I can shift everything over. And then if I get a new report that comes in, I can just drop it into place at the front of the queue. So if you notice, there are a bunch of configuration options in PuppetDB recently around basically time to live for a variety of different objects. And basically, it just does auto expiry once they get to a certain amount of time. So on the one hand, OK, yes, it kind of hand waves over the problem, or it not hand waves over it, but it pushes the burden of some of that decision making onto the operator, onto you. It does kind of force you to think about, well, how much history do I actually want to store? Personally, I think it's good to actually present those types of things as sort of explicit options that users actually get to play around with. Because a lot of software doesn't even bother asking you. And you kind of need to figure it out. And you'll probably figure it out when you get an alert because your disk space has all been taken up. So instead, you just need to think about it. And it's, OK, well, how much do I really need to care about old reports? Do I just want 30 days, 90 days, like infinity? You actually can't set infinity. I was pretty explicit about that. But I don't know. You can put in, when's the world going to end? Like 2030? When's the Unix timestamp overflow? Yeah, this crowd. That joke does not go over well in literally every other venue I've tried to make that in. So that's report storage. Another thing that we could do is, OK, so I've got foo.com, I've got goo.com, and I've got bar.com. But let's say that I'm operating in a pretty elastic environment or one that's highly virtualized. So in that situation, I would basically be seeing nodes come up, nodes drop out. Like maybe I get one set of facts or one catalog or one report for a system. But I never hear from that system ever again. It was up for just a really small amount of time, and then all of a sudden it's gone. So all that data kind of clogs up the works, right? So you start off with these systems, but slowly over time, your infrastructure changes, especially if you're in an environment like you're in EC2 or you're in GCE or you have auto-scaling policies or you have anything like that. I mean, this is increasingly common. So next thing you know, you look at your watch and there's a DeLorean in the parking lot, or I don't know, whatever happens that signifies the passage of time. And really what we do is, kind of like reports, there's also a TTL for nodes that we have as well. So basically, after a certain amount of time, we can say, you know what, I haven't gotten anything from foo.com in a really long time, n days. So we'll just go ahead and make that one immediately eligible to have its storage reclaimed. So we can reuse that storage for other more pertinent information. And that makes it self-regulating node storage, right? So hopefully you're seeing kind of a theme here, which is basically for a lot of these options, again, you have to set them, but it does force you to actually think about how much information do you care about having, what does that working set look like, and you can kind of tune it to sort of match your needs, which I think is kind of nice. So let's say that, so this is all great, except for the fact that storing these things are actually, it's fairly expensive. So for example, how many of you on a system would estimate that you're managing like at least 10 things with Puppet, like 10 resources? All right, how about 100? How about 500? I still see some people, like 1,000? All right, so there's some people, so you can imagine that if I have a pretty big blob, right, that like a catalog that has information about 1,000 resources, like what's inside of it? OK, well, it's every resource, their types, their titles, every single parameter, every single relationship, like require, subscribe, before, notify, pretty much the whole thing. So that entire directed graph is basically squished down into a JSON blob, effectively. And those can get kind of large, right? So you can imagine situations where if all I was doing was giant catalog comes in with 1,000 things, plus each one of those has 10 parameters, plus each one of those has like 10 relationships to other things, both internal and explicitly specified by users. Like all of a sudden, that's a crap ton of data that you have to deal with, right? So that's, that could potentially be a pretty inefficient use of I/O on a box. So let's say that I get a catalog from foo.com. Now, the naive solution here is like, OK, well, you know what? I'm just going to delete the old version, and I'm going to plop the new one directly into place. Because why the hell not? Because that's the easy way to code this up. But that's not super efficient. Instead, what we should do is we should actually make a determination that, OK, well, the new info I'm getting for foo.com, it's orange, and the, well, I guess yellowish, I don't know. RGB value, I got no idea. But basically, it's the same color as what I've already got stored. So that's kind of a metaphor for basically saying that, OK, well, the information I already have persisted for this node is exactly the same as what I've already got. So let's think about that for a second. Is that a fair assumption to make? So in order for that to be true, what that really says is that, for a given system, let's say you're running Puppet every 30 minutes, right? How often are you actually making changes to that system's config that would result in a different catalog for that box? Like, you're probably not coding up changes that adjust the config of that system every 30 minutes, right? Like, I think it's a reasonable assumption. So if that's the case, the theory would then lead one to believe that most of the time, you're probably going to get the exact same catalog for a system that you got 30 minutes ago, or for however long, right? So in that case, I actually don't need to store it. I can just take a fast path, and I don't need to do anything at all. The fastest way to persist data is to not persist it, because it's already been persisted. I mean, it sounds kind of obvious, but I mean, that's a really common trick. And we actually just steal some ideas from Git for a lot of this, where what we do is we actually compute hashes for all these things, not just at a top level, but we also compute hashes basically for every single resource that we have, all the different relationships that we have. In computer science terms, this is known as a Merkle tree. We don't use it's not exactly a Merkle tree, how our implementation is, but conceptually it's kind of the same idea, where you have a tree of hashes that actually makes comparisons extremely quick, and you can figure out just exactly what how they're different. Basically, it's a super fast way to do diffs. And this is kind of what Git and a lot of other tools do under the hood. So we can actually just take pretty quick hashes of all these things. And if we notice that there's a hash match, then we say, you know what? I've already got this thing, so I don't need to worry about it anymore. And it can go along its way. And in the situation that I actually happen to get something that is different, the hash actually doesn't match, then OK, well, that's a situation where I actually have to do some real I/O, and I can actually go ahead and take the pains to store it. So we call that feature deduplication of catalogs. And in the field, we typically see deduplication rates of around, like usually upwards of like 90%, which kind of confirms the hypothesis that we had that the vast majority of times, these catalogs aren't actually changing. An interesting thought experiment would be, what are ways that we could how could we exploit that information to actually make sort of Puppet and the Puppet agent itself, like the compiler, faster if we already know that 90% of the time it's going to produce the exact same output as it produced before? I won't talk about that at all here, but I figured I'd plant the seed because it's a very interesting problem. That's kind of a method of self-regulation that's really designed to make it so that the system doesn't run away with all the I/O that you've got available, right? So we try and be efficient about it. So this is basically what the write pipeline looks like for PuppetDB. And it's definitely a pipeline, like it goes through stages, and basically all writes are asynchronous. Like you send it some data, and then and generally it's pretty fast. It takes maybe tens to hundreds of milliseconds to actually persist that data, but there's no guarantee. So here's what happens if I want to actually post data to it. I do a post, and this is usually the Puppet master that's doing it, but if you have your own, if you write your own clients or whatever, I mean, the APIs are public and documented, and we've got all the wire formats and stuff like that available. But you'll submit your data, that payload goes to an endpoint, and then what we immediately return is we say, hey, OK, everything's good. Or basically, that endpoint will open a transaction to an underlying embedded message queue, so you never have to maintain it. It's not like a separate MQ thing that you've got to deal with or monitor. It's an internal library. So we open a transaction to that. We plop it into the queue. As soon as we get an acknowledgement that it's actually been persisted to disk by the queue, it's not just in memory. It's like actually persistently stored. Then we could say, OK, here's an HTTP 200, and here's a UUID. Which is sort of a handle that you could use to kind of figure out, like, all right, well, if I ever want to see what happened to this, I could correlate that with information in logs and stuff like that. So from inside the MQ, we actually have a different set of processes, a different set of threads internally that'll basically handle actually persisting the data. So we'll have threads that'll pick up items off of the queue. They'll basically handle, I'm going to parse this payload that you've given me. I'm going to try and process it. And if everything goes well, then that's great. It makes it all the way out to disk, and everything's gravy. However, as we all know, like, the world is a terrible place, and stuff is always broken. So let's say, for example, your actual backing, like Postgres database or something like that, happens to go down for whatever reason. Well, normally, OK, the easy thing we could do in terms of coding this up would just say, nah, you know what? Sorry, it's gone. you'll have to send it again. But that sucks, because we already have it, and it's already been enqueued somewhere. So why couldn't we just put it through a standard like retry pipeline? If this sounds like SMTP, that's because that's exactly what it's been patterned off of. Because why reinvent something when, mail kind of works? I know, because I get a lot of it, and I only read like 1% of it. So what happens is if you end up with things like a database crash, or if for whatever reason there's some kind of transient error that results in that processing not succeeding, you can actually just enqueue that information. It goes into, it gets scheduled for a delayed retry. And again, kind of like what SMTP systems do, you don't hammer resend something, to a downstream SMTP server, right? Like you have an exponential backoff where you say, so we do the same thing. We basically say, OK, if it's the first attempt to process this message and that didn't work, then OK, I'll retry it immediately. That didn't work, I'll retry it 2 seconds later, 4 seconds, 8 seconds, 16, all the way to 2 to the, I don't know, like 9 hours. I think it can kind of bounce around in there. And hopefully, the error will actually remediate itself and we could actually process it. However, some situations happen where errors are actually fatal, in which case we just plonk it into a directory called the dead letter office. And what you can do is you can actually look inside of there, and you can get a bit-for-bit copy of the message as it was originally enqueued, along with every single attempt to store it and the full stack trace of what happened that prevented it from being stored. So this has ended up being really useful for purely selfish reasons, because we can talk to users on IRC or on the mailing list that have exceptions in their logs, and they say, I don't know why this data wasn't stored. And we could actually have them, if they want to, they can actually send us the payload from that dead letter office directory, and we can just try replaying it. So if it's a parse error or something like that, then we could actually, it's sort of like, it's like an extremely simplified Wireshark that's very PuppetDB specific. But hopefully that at least conveys sort of the idea behind it. But basically, we can do a replay, and it's much easier to reproduce some of these situations that resulted in the error happening in the first place. So it's not really great to only have a way of writing data, but not actually reading it. So there's a number of different ways that you can query. So let's say that I just want to get every single resource I have for every single system that I've got. And this is an example where I've got basically 4 nodes, and I've got a bunch of different resources for them. And you could actually hit that endpoint on PuppetDB, and it will start streaming to you every single resource with every single parameter for every single node that you have in your infrastructure. And I'll talk. Well, probably won't have time to talk in detail about it, but we do have, it does use genuine streaming under the hood. It streams all the way from a database cursor all the way out using async IO to the HTTP client. So you can actually have like 10 of these running in different terminals, like literally streaming your entire resources in database, and it's totally fine, and it won't blow out RAM or anything like that. So this is good. You have all your resources, but maybe what I actually want is just the services. OK, well, just tack /service on the end. Any Puppet type would work in here. And then suddenly that filters everything down to just the major things that I care about, all the services. But maybe I just want all the food services. OK, well, so you can kind of imagine a natural mapping from the information that we have stored to hopefully a relatively common sense set of HTTP endpoints. But that's not the only one. There's a pretty huge variety of them. For example, if I want to actually slice and dice this information, starting with the node at the top level, like I just want to know something about foo.com's resources. So OK, I can go to /nodes, foo.com, /resources. So I get all of those. But maybe that's not actually what I want. And what I actually want is just the packages. OK, well, that's fine. I can just display both of those. But maybe I really just want package foo. OK, so there I go. And that's kind of a quick way to just get access to information about your infrastructure without really having to do a huge number of fancy tricks, right? Like you don't have to open up a SQL prompt. Like if you're on a system with curl, like it'll generally work. And those APIs are documented, and you can see how they all work. So using that mechanism, you can query facts, nodes, resources, reports, events, and all kinds of internal metrics about PuppetDB itself. There are also a number of advanced queries that you can do via kind of an AST-based language. It's more meant for kind of API use and sort of machine-to-machine communication, because you probably don't want to handwrite it. If you really want to know why you shouldn't handwrite it, you should go to Danny's talk, which I think is going to be later today, where we'll probably talk about that. But all those facilities are pretty well documented. And through that facility, you can do things like aggregates, ordering, you can do paging. As I mentioned, all of the information is actually streamed out. And you can do things like subqueries. So I can actually correlate information about resource. I want to get all the versions of Apache running on Linux systems that happen to be running kernel version this, that have had a Puppet run in the last 30 minutes where the status was something changed. Like you could get that level of detail if you really wanted to. Which is cool. So hopefully the possibilities are pretty open for interesting tools that could leverage those kinds of things. And like I said, a lot of this stuff is, or pretty much all of it's actually documented, and it's on docs.puppetlabs.com. So I encourage you all to check it out. So that's kind of a quick recap of what PuppetDB is, roughly how it works, and some of the features that I think make it not a total nightmare to manage operationally. So what's happened since the last time we spoke, which was here, like literally here a year ago. Well, San Francisco a year ago. So at the time, I think we had just released 1.4. Based on our metrics, there are around 11,000 deployments. Not downloads. I mean, who knows? It's tough to measure anything with download counts these days. But actual installs. And we had some basic streaming support and a couple of endpoints, and maybe a couple of other things I'm really not remembering right now. But the good news is that we've actually been busy, and we've been doing things. And by we, I mean not really me writing a whole lot of this stuff, because now there's a team of people that are much smarter than me doing those things. That's Ken Barber, Ryan Sr., and Wyatt. They're all on IRC, so you can talk to them if you have complaints or feature requests. So we've been doing a lot of stuff. And I'm going to go through. I mean, it's kind of all over the map. And a lot of this effort was done in part by community feedback, people finding bugs, people actually trying stuff out, and then letting us know what actually didn't work. In particular, things like performance lag, or just I don't think we've had any deadlocks or anything crazy like that. So that's been pretty good. And I think correctness has generally been pretty great. But I think it's more that it's really difficult for us to test a lot of these things in isolation, especially when you're trying to throw a lot of load on the system, because ultimately, our ability to test a wide variety of configurations inside of Puppet Labs is fairly limited, right? We can only test we can make best guesses about how people are actually going to use the system. But ultimately, what really adds a lot of value is getting this out to the open source community, where they can throw a ton of load at this, a ton of really weird-looking data, and we can actually figure out the right way to tweak the system to actually make it better for people. And all of this is documented here, if you really care, and you could go through all the release notes that we've had since 1.4, and it's a ton of stuff. Out of all those, the only feature I really wish we actually legitimately did implement was bringing Eris back to life. Right? Just use a Phoenix down. You have I don't know, 99 of them in your inventory. I don't know. So I'm going to try and highlight a couple of these that I think are particularly interesting. First is differential storage. So recall from way back, 6 minutes ago, when I mentioned that we do hashes of these things to actually determine whether we have an exact copy of it, and if so, there's no need to actually store anything. And only when they differ can we actually do the storage. So that's great. No, that's OK. So what does a catalog actually look like? So it's not just an opaque blob that's efficient to store, right? It actually is comprised of a fair number of kind of components, right? So for example, it's comprised of a number of different resources. So let's say that I already have a bunch of those resources, either for this node, maybe for other nodes, because chances are you probably have some Puppet code, like a module that you aren't using on just one system. You're probably using that on 100 other systems, that they're all your web servers, right? So if I already have all of these, and then bar.com's catalog comes along, and then it wants to store a bunch of these, because the hashes don't match, right? So there is a difference here. Why would I waste my time actually storing things, even if a subset of them have already been stored, right? So really, the smart thing to do here is actually try and match up what's been stored and what needs to be stored. So we basically go through, and this is why I said that we actually have hashes that kind of go down a couple of levels, because we can use that to do quick comparisons between all the individual resources that we have. So here we can see that a number of things match up, right? OK, those files are definitely the same. These packages are the same. They're the same because they're the same color. These services are the same. Something's going on with bar, but so basically we end up with 2. So there are 2 mismatches here, right? So we have bar, and then we've got service. I don't know what comes after goo, so I just put zzz. So here what we can do is we can basically say, OK, well, the current catalog for bar doesn't make any reference to service bar, so I don't really need to store that anymore, so I can destroy that. But what I can do in place is I can actually plop in this new guy that I actually care about, because it's relevant data that's up to date and timely. So that's good. So what that means is now suddenly, instead of doing I/O for all of those resources, I'm only doing I/O for 2 of them. One set of deletes and then 1 set of inserts. So that significantly reduces how much I/O we actually need to do. This also works for edges and facts as well. We kind of implemented the same algorithm. And essentially what this is doing under the hood is it's just trading reads for writes. I mean, we basically have to read in the data that's currently stored for a system, whether it's facts, whether it's edges, whether it's resources, et cetera. And then we have to do some computation. And then based on that computation, we save ourselves some writes. In practice, I think this turns out to be a pretty good trade-off. And in the field, what we've seen is basically, after we implemented this, and by we, I mean, I think it was mostly Ryan and Ken that implemented this, we've seen anywhere, around like 90% drop in writes, which is pretty amazing. This was a graph that the Spotify folks actually gave us. And you can kind of see, this is basically, you can see reads and writes that are plotted on here. So you can kind of see the load that was on the system beforehand, and then all of a sudden, they do a database. This all rolled out in PuppetDB 1.6. So you can see they actually rolled it out. So of course, that's an I/O spike because we have to do some schema migration. But as soon as that actually happened, now the writes basically go way, way, way down. And reads actually, because the system isn't as starved for I/O, become a lot more predictable and less sort of wobbly. So that's great. Like I love that graph. So I definitely wanted to give a shout out to Spotify and the other people in the community, Danny, other folks that helped actually test the stuff and let us know, that there was a performance improvement. More effective deduplication. So like I said, the key to a lot of this dedupe is basically that we can compute these hashes for things. But it turns out when you compute hashes, order actually matters, especially if you're computing a hash of an unordered thing. So say, for example, I've got 2 hashes that should be semantically identical, foo map to goo, bar map to baz. If I actually flip the order of those, it shouldn't matter because hashes normally are unordered structures, right? Semantically, they mean the exact same thing. We actually weren't super careful in the early versions of PuppetDB, and we had a very naive algorithm for actually computing hashes for these things that didn't take into account that they were unordered. So depending on how many times you were computing this hash in a row, you could end up with a different order. You'd end up with a different hash, which results in us doing too much work, right? That results in false negatives. We think that these hashes don't match, but in reality, they do. So it's not a disaster because it's not like we're operating incorrectly. We're not throwing away data. We're actually storing data when we don't need to be storing data. So this is a situation where we could have improved upon things, but we didn't. So of course, we fixed that. What that immediately led to was about a 60 to 70% boost for users that would have, we would end up with users that would say, I have like a 0% dedupe rate. Like, what's going on? This thing's eating up my server. And that was really difficult to debug. And I would want to give a shout out here to the people at CERN that actually helped us debug this. They were really, really helpful. And we actually put in some features that make it easier to debug if you're experiencing this yourself. Of course, in true software fashion, once we actually put in the feature to help you debug it and we fix the bug, no one has run into this bug anymore, so no one has used that extra debugging feature, which makes me a little sad. But what can you do? Hot standby support. So, if you've got a PuppetDB daemon, it does reads and writes to a backing Postgres. That could be, one of your own choosing, or it could be RDS, or it could be whatever you want, right? What a lot of people will do is they'll set up well, not if you're on RDS, I guess, but if you aren't, a lot of people will set up a hot standby and they'll do streaming replication to the standby. So what we did is normally, you set up your standby, PuppetDB doesn't know about it, so it doesn't take advantage of the fact that you've got a perfectly good database that's not actually seeing that much write load. So why can't I take advantage of the I/O that's available on that system, right? So what we've put in into, and I think this also went into 1.6, or maybe it was in 2.0, but we put in hot standby support, which allows us to do things. We can actually have PuppetDB point at the standby just for reads. And because, again, the way that write pipeline works and how it's rigorously segmented from the query pipeline, we actually know a priori which queries are going to be read-only and which queries are going to be read-write. So we can actually direct things to the standby. And I think it was State Farm that actually helped us really tweak this and get that tuned. And that helped a lot. Like, they saw a really huge improvement in reduced I/O contention and much better throughput from their system. Environment support. So I've got foo and I've got bar. Foo is in Puppet environment test. Bar is in Puppet environment prod. Now I've got a bunch of resources that happen to be stored. These are foo's resources, and these are bar's resources, helpfully color-coded. Foo says, I would like all files, please. To which PuppetDB says, I will do anything for you. And it will give foo back a file resource from a different environment. Maybe that's what you intended, maybe that's not what you intended. What I do know is that prior to PuppetDB 2.1, you didn't have an option. You basically got back all the data for everything, and I really hope that's what you wanted. But in case that wasn't what you wanted, you know, everybody ends up sad. He's trying his best. I had a lot of other lines in there like, I just want to be friends, and then I actually felt kind of sad. Don't anthropomorphize the software that you create. Like real human children, they will only disappoint you. So what environment support allows you to do is you can say, I want all files for environment test. PuppetDB can say, all right, well, now because I have some environmental awareness, I can just hand you back the things that are germane to the environment that you have. And we're friends again. So all data that's been transmitted or received now includes the environment, whenever we can get it. And queries can be isolated to a single environment. Unified querying. So this is going to be pretty quick. But basically, internally, the structure of our code, because it was an amalgamation of query capabilities over time, ended up duplicating a lot of logic depending on what type of information you were trying to query. So a query comes in, and then depending on whether you're looking for facts or resources or reports, it would basically go through kind of not quite a carbon copy, but a bespoke parsing and analyzing pipeline that would actually compile that stuff down to efficient SQL. And at the time, I think we thought that was a good idea because maybe we could make more efficient decisions about how to compile this down to talk to a database. But in reality, what ended up happening is if I want to add a feature to one of those endpoints, like regex support on strings, sometimes we just weren't diligent about making sure that it was pervasive through all of those endpoints. So you'd end up with this weird mishmash of operators that were supported on a subset of them, but not all of them. So of course we did the logical thing, right, which was we consolidated all of it into a single pipeline. And what we did to extract efficiency out of it is we kind of put in sort of a standard compiler trick, is we can basically get queries that are in there, we can parse them, we can rewrite them now that we have some knowledge about the types that they're actually going to be going against, whether they're singletons, there's arrays, are they chars, are they integers, et cetera, et cetera. We can apply operators in a unified fashion and compile that down to SQL. So that means that all these operators are now uniformly available across everything, and we could add new endpoints faster. So that improves our speed. Structured fact support. This is what a structured fact looks like that I kind of made up. But it's basically, instead of flat strings in newer versions of Puppet, you can actually have structured data as the payload for your fact. And this actually makes more sense because everyone hates interface IP address underscore ETH0. You know, that's stupid. It should just be IP addresses, and then you can hash into it. So at the AST level, you can actually do queries here where I want to get the first MAC address for ETH0 as part of the networking structured fact. So OK, I just want to get, basically you can do a path operation here, and you could say that's the one I want, and you give all the path components that you care about. We have regex support in here as well, so that if you say, look, I just want every MAC address from any ETH interface on any system, then you could put that stuff in there as well. Regexes are normally slow with databases, but Postgres has a pretty neat feature called a trigram index, which I didn't know existed, but it's an interesting set of papers if you like algorithms. And it basically breaks down words into triples, and it could use that. It compiles down a regular expression into an automata, and it could basically leverage the trigram index to speed up regular expressions to make them extremely fast, which is pretty sweet. So where are we now? So hopefully, you will realize that we've added a lot of features, but we've also added a lot of speed. Right? And I'm actually pretty proud of that because normally software kind of bloats over time, and I'm actually pretty happy that the stuff has actually gotten measurably faster over time because I want to write the software that I would like to use. We have a lot of language bindings that are pretty actively maintained. There's Ruby bindings, there's Python bindings, we've got JavaScript, there's C, C++, so if you want to have libpuppetdb.so, totally exists. Bindings in Go, we have Clojure ones because PuppetDB is written in Clojure, Java bindings, et cetera. It runs on the Trapper Keeper service framework that we wrote. That's the same underpinnings for the new Puppet server that's also written in Clojure. A lot of it was extracted out of PuppetDB, and it's kind of a unified way of sharing a lot of that code that turned out to be pretty successful. So it's a good way of kind of compiling logically separate services into the same process, or you can separate them out depending on your deployment needs. There are great tools that are writing on top of the PuppetDB API. There's PuppetBoard, which there's going to be a talk on that a little bit later, which is outstanding. I highly encourage you to take a look at that. The people from Spotify wrote Puppet Explorer, which is kind of a similar take on it, also using the API. And there's basically, based on our numbers, there's a new deployment of PuppetDB every 10 minutes, which is an improvement over last year where it was a new deployment about every 20 minutes or something like that. So that's slightly terrifying, but it's also pretty cool. Coming soon, more efficient GC. So basically, we want to make it so that that space reclamation process is much more efficient than it currently is, because right now we do it in bulk every 30 minutes, and that turns out it can potentially throw off the statistics system inside the database, which slows down queries and use of indexes. So we think we could do it more just in time, which I think will make things faster. We're going to be working on simplified query syntax so that instead, for advanced queries, instead of having to put in a giant AST that really is meant for machines to use, you can instead use a more natural language one. Danny's happy about that. And we're probably going to be leaning heavily on the work that Spotify did in their libraries, because they've implemented one of these. We want to start taking a look at storing historical data at a minimum, so people could do things like store diffs for catalogs, like what's actually changed since the previous version. But that's it. Other than that, lots of other stuff coming, hopefully a lot of activity. Thank you. It's open source. Try it out.